Start.
You ready?
Yeah.
Alright, good morning everybody. I'm going to be presenting my project on gait generation for quadrupedal walking robot. So, over the past few decades we've seen significant improvement in the space of legged robotics. Here we can see Boston Dynamics' famous Spot Mini as it seemingly easily traverses over this flight of stairs. I can always guarantee you this wasn't the first take of this video, and this wasn't always the case. But the question is, why legged robots? Quite simply, legged robots are able to traverse or navigate terrain that would have seen previous traditional robots such as wheeled and tracked robots fail. Of course you can design task-specific robots such as tracked robots that are capable of specifically designed to go over stairs, or robots which have two massive propellers attached to them allowing them to fly over walls. But in reality, when you introduce these kind of task-specific robots into other environments, they quite often fail. The opposite is almost true with legged robots. As we develop and increase our technologies, we find more and more tasks that are suitable for these robots. So what's special about Dogbot? Dogbot is a quadrupedal robot developed by Robotics for the sole purpose of implementing and testing machine and reinforcement learning algorithms. Now, you may be thinking, Dave, you've just showed me a video of Spot Mini climbing up those stairs. Why have you decided to, or why are you developing this gait generator for Dogbot? Well, because Dogbot is a unique robot with unique physical properties, unique dynamics, and unique sensory capabilities, it essentially required its own bespoke high-level controller. Of course, you can gain inspiration and use principles and theories from existing technologies, but it required its own, as I said, unique controller to be developed and to control this specific robot. So using this information in the background, I defined the aims of this project, and these aims were the controller needed to be able to generate multiple gaits, it needed to be maneuverable in all directions, it needed to be autonomously or manually controlled, and to some extent be robust, perturbation resistant, and able to traverse uneven terrain. Alright, so before we jump into the method and the detail, I've decided to show you an overall view of the high-level controller. What's important to see here is that you've got 5 main threads which make up the controller. As I explain this controller, I'm going to use a bottom-up approach, starting on the simplest level, focusing on the main controller, and in fact focusing on how to actually calculate the joints required to move a leg in order to perform certain tasks. Thereafter, we're going to be increasing the complexity, and we'll focus on the other threads which can be activated or deactivated depending on the task that you wish to perform. So starting with single leg control, the first thing that was done was developing a trajectory generator or trajectory function. Now this function was called a composite cycloid trajectory function, which was slightly improved upon in order to allow the starting position of the trajectory to be in the middle of the stance phase. We'll explain why this is important later. But what's important to notice about this trajectory function is that you can input the step height, step length, step period, swing period. Essentially, you've got all these different parameters that you can play with in order to achieve a step that you would require. Additionally, you use the current time, which essentially determines where in space the endpoint is. This is quite an important diagram, which we're going to come to again later. So here you can see a very simple two-dimensional video or animation of the step taking place. Here you can see it's just a simple, quite a long sagittal step length. What I've done here is this is just to show you can quite easily change the step parameters. So maybe in this case you wanted to back step over something quite high. This two-dimensional step was then improved upon, and a three-dimensional step was created. How it was done was simply by adding an additional step in an orthogonal direction. So as you can see here, you still maintain that composite cycloid trajectory, and we've got another composite cycloid trajectory in the transverse plane. So if we actually animate this, you can see how the resultant is a new step, still maintaining that shape, and if we then look at the step from in the sagittal plane or the transverse plane, you can see how that same step trajectory profile is maintained. So that's from the sagittal profile or sagittal plane, and the transverse plane, you can see it over there. Here in the next video, which is going to come through just now, I'm just showing you a similar example as what I did before. By changing the parameters, you can step in any direction, any distance, Here we've got a short sagittal step length and a long transverse step length. What this essentially allowed you to do is define your endpoint positions. Once you've got your endpoint cartesial positions relative to the hip of the robot, your x, y, and z coordinates, you can use three-dimensional inverse kinematics to calculate the joint angles required to perform a certain task. These are the calculations that we used. Alright, so time, the when becomes the how. So back to this graph, what this diagram is essentially showing you is that this is a very simplified version where you've got a time vector that goes from 0 to 9, and it's a discretized example. So what you'll do is you'll essentially iterate through this time vector, and based on where you are in the time vector, it'll define where you are in physical space. Why is this important? Well, if we look at gait graphs, in order to generate gaits, we used a method called gait graphs. And if you think about what a gait actually is in a four-legged robot, it's the synchronization, a certain pattern or synchronization of the endpoints of the four robots. So in the trotting example, the front right and back left legs will start in the swing phase. You can see that the blue illustrates the swing phase. That'll then go on until the back right and front left legs will then initiate the swing phase. What's important to notice here is how you can essentially therefore define the timing offsets between the front right or some relative leg. You can define a timing offset, and using this timing offset you can synchronize your timing vectors of the four legs, allowing you to generate these different gaits. So here's just another graph that I've used or another diagram that I've used to further explain this. I've kind of superimposed those previous timing diagrams onto these gait graphs, where we're looking at a particular instance here where your back left and front right legs are about to initiate the swing phase, and your front left and your back right legs are about to initiate the stance phase. You can see here your back left is at, in this theoretical example, position number 3, and your front right's also at position number 3. Likewise, your front left is at 8 and your back right will be at 8. This is obviously a very simplified example just to illustrate how the system works. And there we go through it. Okay, so at this stage, the controller had the ability to, each one of the legs could step in any direction, depending on the parameters that you define. But there was no way to actually map the rotational translation of the body into these particular step vectors. So a function was then defined to map a body rotation to a step vector. So as you can see, if you had to rotate anti-clockwise by theta degrees, this would show you the step vectors that you're required to take in order to get to those new positions. Using those step vectors, or essentially you then can extract the sagittal and transverse step lengths. Using the transverse function the trajectory function that we previously described, you get the endpoint positions. Using inverse kinematics, you can then get your actual angles required to perform a certain task. The same then applies for both a translation and a rotation. And here's the simple linear algebra equation that can be used to calculate these step lengths. So if you wanted to perform some kind of motion like this, the exact same applies. Here's the robot, the simulated version of the robot, actually demonstrating this. You can see here it's just rotating. Essentially now it's translating forwards, so walking forwards or trotting forwards, then translating to the right-hand side, translating to the left-hand side. And also what it now demonstrates is the ability to adjust the height of the robot. Again, this is just done by sending in step parameters into the trajectory generator, and the process kind of repeats itself. This is showing a similar version, but on the physical robot. Here the robot's rotating again. So this is how the maneuverability of the robot was designed. Now, a very important point in the project was reached, and that was about change. What happens if your current step length is 50 centimeters and you want to increase to 100 centimeters? You've got many different ways in which you can do this. Now, what you could do is switch from a step length of 50 to 100 centimeters between your full gait cycles. So complete a full gait, then once you're back at the starting position, start your new gait. This would be good because you'd have no discontinuities and you wouldn't have jolty motion. However, your robot would be very unresponsive. You'd give it a command, it would have to complete a full gait cycle before it could move on to the next step. Another option would be to change within gait cycles. Now, this would be good because you'd have a very responsive robot, but you'd experience this significant discontinuity, which would lead to jolty motion. The simple solution to this was an algorithm which essentially tricked the robot into thinking, instead of making these large parameter changes, it broke up or discretized these parameter changes, resulting in a really nice smooth curve function, and while maintaining a highly responsive robot. Here's an actual graph which was used using the state feedback from a robot, making a step change from a step length of 50 to a step length of 200 centimeters. Now, it's a massive change. You can see the green trajectory represents the resultant trajectory. You can see it's really smooth and it removes the discontinuities. Here, I hope I can get sound because this is actually how I realized what was going on. Let's just see, I don't think we've got sound yet. But you can kind of see in the motion here how jolty the changes are between the robot. This is changing the step parameters without the step interpolation algorithm. Using the interpolation algorithm, you can see the motion's far smoother, and it allows you to make these maintain responsiveness. Of course, here there's a trade-off between responsiveness and jolty motion, which you have to just define depending on your task. Okay, so at this stage we had a fully functional open loop controller, so it was not resistant to perturbation or any kind of any disturbances. So in order to do so, or in order to add some kind of feedback component, we embedded an IMU on both the simulated version of the robot and attempted to embed it on the physical robot. This allowed us to control the yaw, control the roll and pitch, and add a push recovery method. So I'll first be discussing the yaw controller. Two separate yaw controllers were essentially developed. The first was a manual yaw controller. So this is quite an interesting case. This is the case where you're controlling the yaw of the robot using the Xbox controller. So what would happen here, this is actually an unusual control diagram. As you can see, the yaw state leads the set point, and only after the yaw state is settled do you define your actual set point to be maintained. What's happening here is that as you're using the Xbox to control the robot, you'll move it to a desired position, you'll visually see the position of the robot, and when you're happy with the position of the robot, you can release the controller. The robot then realizes that it's not receiving any more inputs, it saves the current position and locks that position. How I've demonstrated that is by resetting, once the set point has been defined, I reset the yaw to the 0 position, and you can see how the robot then maintains or goes back to that previously saved position. So this is demonstrated in this video here. So I would have used the Xbox controller to define or visually define a position, then manually resetting the model position, you can see how it goes back to the saved orientation. So the second yaw controller was an autonomous yaw controller, which is a much more conventional yaw controller. You'd simply just define set points and the robot would tend towards those set points in a very kind of traditional conventional method. Okay, now to something slightly more fun, the roll and pitch controller. So the roll and pitch controller was designed to improve stability when traversing uneven or inclined terrain. The theory behind the roll and pitch controller was that inspiration was drawn from how quadcopters are controlled, is that it was attempted to minimize the roll and pitch angles, and this was done by calculating the relative offset between each individual hip and a horizontal reference frame that would exist if there was 0 roll or pitch. So how I did this is I assigned an individual PID controller to each one of the leg joints. You then calculated the vertical offset between the respective hip and the horizontal reference frame, and you adjusted the height of the legs accordingly to maintain 0 pitch. So here's an example. So in this previous example, you just see how the robot would be unbalanced, and then after the roll and pitch controller has been set to work, it would, in this theoretical example, it would decrease the height of the front legs and increase the back legs. Here's a video showing this. So first we see an example of the robot working without the roll and pitch controller in place. You can see that it really struggles, often falling over, attempting all the different terrains. Then once we activate the roll and pitch controller, you can see how it's, in this case, it's adjusted the left legs and the right legs to maintain horizontal pitch, allowing it to actually walk on a step incline. The same occurs when you induce a pitch and you step onto a box. You can see how it adjusts the legs, and then when it moves off, you can see it controlling itself and regaining that stability. If we then tackle the big uneven incline, I've had to speed this up because otherwise I'd have you guys here for ages. But the robot gives it a go, and it adjusts the front legs so that it can, again, maintain that stability. So I've actually sped it up here, and we can watch it taking the whole incline. Here we go. Then what's interesting is that using the same controller, you can actually descend steps. So it's able to descend steps perfectly as well, essentially blind descent of steps. And then you can see it maintains its stability by readjusting the back legs. Then we moved on to the push recovery method. The push recovery method essentially consisted of two components which could be used. And the first component was the push detection method, and the second was the defense strategies. So the pushes were detected using the lateral accelerations experienced in the body. However, it was found that using just the instantaneous accelerations wasn't good enough to detect the force. So a window detection method was used in order to essentially average the previous however many acceleration values that you feel is necessary. So assuming a IMU publish rate of 100 Hertz, if you use a window size of 0.06 seconds, you'd consider the previous 6 accelerations and you'd average those up to try and detect whether or not the robot is experiencing a force or an acceleration. So in order to test this, or in order to determine which was the best or most appropriate window size, I tested for a number of different window sizes. I found that a window size of 0.8 seconds worked the best. So here you can see the average acceleration at this time. So this is the gait cycle simulation increments, where 1,000 represents essentially 10 steps. So the robot's able to the robot maintains stability. It then experiences a force, and here you can see a rapid incline in the accelerations. So using a window size of 0.08 seconds, you could then define the push threshold. So I defined it as 4 meters per second squared, and in that way you can determine whether or not the robot's experienced a force. This was then tested using a number of different forces and durations. So forces ranging from 0 to 100 newtons for 0 to 1 second. You can see that in every case a force has been detected. So again, the force was applied here, and in all cases the forces were detected. Then came the fun part, where you had to actually decide on the defense strategy that you'd use. So a couple of different defense strategies were attempted. One of the more successful ones was, so we're going to see here now the robot being pushed without the defense strategy in place. You can see it just falls over. Pretty poor. Of course, it's not even walking yet. So as you'll see, the defense strategy that was the most successful was reducing the height of the robot, increasing the transfer step offset, and actually step in the direction opposing the force. This resulted in quite a robust solution, and the robot was able to essentially take quite a beating without falling over. You get the idea. All right. Finally, the Bayesian optimization hyperparameter search. As you increase the complexity of the controller and you add on all these different layers, what happens is that you also increase the number of parameters of the controller. What I found is that slightly changing certain parameters resulted in significant improvements or reduced the performance of the robot for certain tasks. So this actually created the perfect scenario for Bayesian optimization hyperparameter search, because you need to tune these parameters, and extracting data points is incredibly expensive. So what I did is I essentially created a theoretical function, a task-specific function. So I focused on 2 different examples, one ascending an uneven incline and another trying to defend against multiple different forces. I then created a theoretical reward function, so a task-specific reward function. So for example, when ascending the incline, the reward function would be based on how far the robot went and how long the simulation went on for, and how it maintained stability, etc., etc. For for defending against forces, the reward function was based on the total magnitude of forces it experienced, as well as the time that it survived for. So using this, you essentially create, as I mentioned, a function which was the simulation which you try and optimize or improve. So here's the robot just attempting to fine-tune the parameters for force detection. So here what I did is I applied random forces in random directions for random durations, and as the robot survived for longer and longer, I would increase the magnitudes of the forces. In general, in terms of the Bayesian optimization process, quite frankly, there wasn't enough time to perfect the process. I have no doubt that such a process would be really valuable for fine-tuning these parameters, but there were a number of problems that were run into. One of the main problems was based on perhaps the simulation environment, where seemingly good parameters would yield poor results, completely skewing the optimization function. So a way to get around this would be to sample multiple sets of parameters, or sample sets of parameters multiple times and choosing the best set of parameters, based on the premise that it's highly unlikely that poor parameters would result in a very good reward function, whereas good parameters did tend to lead to poor reward functions. So here you can see the robot's just attempting different kind of parameters, and here you can see the reward function and the various different parameters that have been attempted. So that was the Bayesian optimization hyperparameter search. All right, and that's the entire method concluded. Onto a quick discussion and final thoughts. As most of you know, the reality of the physical robot is that it was one of the earlier iterations of the mechanical design. One of the main problems here, aside from the obvious, is that without physical robot testing time, you're unable to determine whether or not instability is caused by the hardware, is caused by poorly tuned parameters, or caused by the controller itself. Secondly, were the aims of the project achieved? To an extent they were. The robot was, multiple gaits were generated, so walking and trotting gaits. The maneuverability was achieved. It was autonomously or manually controlled. Was it fully robust and perturbation resistant? You really can't say. I mean, the nature of such projects can be far more improved than this. So I think a lot of work can be done there. Other major problems. One of the major problems experienced with this robot, I think, was the fact that it was using pure position control. So the robot had no idea whether or not it was making contact with the ground. So if it experienced even a slight roll or pitch, if it was still in the stance, in the swing phase, it would essentially push itself away from the ground, further increasing instability. So I think that this was one of the major problems of this current design of this controller. There are a number of ways to deal with this. One way would be adding tactile sensors onto the feet of the robot, acting essentially as a Boolean switch, determining when you should transition from swing to stance phase. One other problem was obviously the slippage of the feet. This made it really difficult to control the physical robot and see whether or not it was working properly. Final thoughts. I think the controller that exists here, in terms of the gait generator and the maneuverability, is highly modular, and it is very likely to be and able to be used and developed upon further in research. The higher level tasks like the roll and pitch controller, the push recovery method, I think can definitely be improved upon, and different strategies and different techniques can be used. But all in all, I think it's a decent controller that can be used as a base for further research, as well as we've seen, potential machine learning or reinforcement learning algorithms. And that's it. Thank you very much for listening.
Okay, that was excellent.